Hello everyone, and welcome back to another video of Total Organic Chemistry. This time we're going to be taking a look at elimination reactions, and we're going to start by looking at E1 reactions. So by the end of this video, the questions that you should be able to answer are: how do E1 reactions occur? So what is the mechanism? And then also, how do elimination and substitution reactions compete with each other? If you need any additional review, or if you'd like to look back at the mechanisms of SN1 or SN2 reactions, please feel free to subscribe to my channel and take a look at those videos that I've uploaded on those topics. So let's start with a familiar mechanism here. First, we have this tert-butyl bromide that we have studied before, and let's draw a mechanism for the SN1 reaction of this tert-butyl bromide with water. So we know that from SN1 reactions, we first have the bromide leaving group falling off, so we'll draw that arrow towards the bromine here, and that generates the tertiary carbocation. So we have this plus charge on the carbocation, and then we know that our water molecule with the lone pairs on the oxygen will come in to attack that carbocation, giving us this adduct with a positively charged oxygen. And then we will have another molecule of water pull off that extra hydrogen to give us our final product of the tert-butyl alcohol. So hopefully you should be familiar with that SN1 mechanism, but let's take a look at another thing that could also happen. So if we go back here to the first step, let's draw another arrow to generate that carbocation again. But this time, instead of attacking the carbocation and substituting the bromine, what could also happen is this water molecule can pull off one of these adjacent hydrogens to the carbocation, and then this bond to the hydrogen will swing over to form a double bond here, and then that water will come off, so we end up with this alkene here. And this second mechanism is called an elimination, because we have eliminated the bromine and one hydrogen from our haloalkane. Specifically, it's called an E1 reaction. So E1 stands for unimolecular elimination, just how we have SN1 that means unimolecular substitution. And the important thing to remember with E1 reactions is that they will always compete with SN1 reactions when possible. So we have the same rate determining step, like I said, that's the formation of the carbocation, and then after that carbocation forms, either the substitution or the elimination reactions can occur. Let's draw a slightly bigger molecule here. We'll have this sort of larger haloalkane. And we're going to say that the leaving group will be chlorine in this case. And let's draw out the possible products when we treat this haloalkane in methanol, and let's say we'll heat it up a little bit. So hopefully we know that for the substitution reaction, the chlorine will just be substituted by an OCH3 group, so that methanol will come in just like the water does, but instead of an OH group from the water, now we have an OCH3 group, a methoxy group, from the methanol. So that is our SN1 product. But in fact, we can have a few different E1 products. So if I label some different hydrogens here, we can label these methyl hydrogens black. This hydrogen here can be blue, and this one over here may be red. And because this molecule is asymmetrical, so different than the tert-butyl bromide we had earlier, this molecule is asymmetrical, so we can eliminate any of these three hydrogens to make different products each time. So you can imagine if we eliminate the blue hydrogen here, we'll end up with this alkene, so the double bond will form between these two carbons here. If we eliminate the black hydrogen, then we'll end up with this sort of terminal alkene. And finally, eliminating the red proton will give us this other internal alkene, different from the first one. And these could all be plausible E1 products from our reaction with methanol, because all of those protons are adjacent to the carbocation that would form, and therefore they could be eliminated to form these alkenes. So whenever you have a molecule and you're looking at the E1 products, it's very important to look at where all of your hydrogens are, and to see if multiple products can form instead of just one elimination product. I'd like to talk about one more property of E1 reactions in this video, and that is the matter of entropy. So to demonstrate this, let's go back to the first reaction we looked at with the T-butyl bromide. And let's start with a balanced reaction for the SN1 product. So we start with the T-butyl bromide, and we add a molecule of water, and then that produces the product, so the T-butyl alcohol. Plus we know that Br- is the leaving group, so we'll have that on the product side. And then also remember that we need one extra molecule of water to pull off that proton in the last step of our SN1 mechanism. So let's actually add a 2 in front of the H2O here on the reactant side, and then that will produce one extra molecule of H3O plus on the product side. So we end up with 3 products, T-butyl alcohol, Br- and H3O plus. But we also have 3 reactants. So we have the 1 T-butyl bromide and then 2 molecules of water. So what does that have to do with entropy? Well, whenever you have more molecules, that system will always be higher in entropy. And we know that entropy likes to increase overall, but in this case we have 3 molecules going to 3 molecules. So this SN1 reaction is actually entropically neutral. So we have no tangible gain or loss of entropy in this reaction. Okay, so let's look at the E1 reaction now. So we still start with the T-butyl bromide, and then also another molecule of water, and then this will go to the alkene. So remember, it's an elimination reaction, so we'll always form an alkene. And then again, we'll have the Br- leaving group. But what's different this time is that we don't need an extra molecule of water because there's no proton to pull off in the last step like there was in the SN1 reaction. So we do end up with a molecule of H3O plus on the right side. That's from the second step where we pull off the hydrogen to eliminate to the alkene. But that is our only molecule of water we need. So for the E1 mechanism, we start with 2 molecules, the T-butyl bromide and 1 molecule of water, and then we end up with 3 species. So we have the alkene, the hydronium, and the bromide leaving group. So this E1 reaction is actually entropically favorable because it increases entropy. We have more molecules, higher entropy. Okay, so we know the E1 reaction is entropically favorable. So what does that mean for this competition between SN1 and E1 reactions? Well, if we go back to the equation that we have for Gibbs free energy, so we have delta G is equal to delta H minus T delta S. So that relates our Gibbs free energy, delta G, to the change in enthalpy, so delta H, and temperature T and delta S is entropy. We know that if you increase the temperature, then this delta S term will become a lot more important. So if you have a very, very high temperature, then this delta S term is going to matter a lot more because it's being multiplied by that temperature. And we know that the delta S term is basically 0 for an SN1 reaction. That's what it means to be entropically neutral. But the delta S term is going to be positive for an E1 reaction because we have that increase in entropy. So what that means for us in the end, the very important thing for organic synthesis or organic chemistry, is that if you increase the temperature of an SN1 reaction, you will actually end up with a higher percentage of an E1 product and lower amounts of the SN1 product. So if you ever want to push a reaction to make the alkene, so to the elimination reaction instead of the substitution one, then you really want to heat that reaction up and conduct it at a higher temperature than you would for just the SN1 reaction. So that concludes my video on E1 reactions and the mechanism by which they proceed. If you liked this video or learned anything, please subscribe to my channel and take a look at my Patreon page that I will link in the description, and that really helps me to continue creating these videos and making content for you to help you learn about organic chemistry and perform well. Thank you for watching.